Let us continue our class from torque speed characteristics curve. From our previous lecture, we saw the torque equation under running condition can be written as 3 over twice pi ns into slip s into e2 prime square into r2 divided by r2 square plus s into x2 prime square. Here, for a constant frequency supply, this 3 by twice pi ns is constant. For squirrel cage case R2, rotor resistance is constant. We cannot change rotor resistance. And x2 prime and e2 prime, both of them were having constant value for fixed supply, as they are having the value at standstill condition. And S slip, this will be varied when the rotor speed varies. When the rotor speed increases, the slip value decreases. When rotor speed decreases, slip value increases, as we saw in our previous lectures. And we saw that if we draw this characteristics curve in x-axis, if we take the rotor speed, in y-axis we take tau r, then the characteristics curve has this type of shape. This is ns value, ns equal to nr, though it is not possible for any induction motor to reach nr equal to ns value as motor condition. Here the value of nr is equal to 0. At nr equal to 0, the torque exerted on the motor is named as starting torque. And we described in the previous class that the motor will produce exactly same amount of torque equal to the load torque. So if we consider a three-phase motor, induction motor definitely, suppose this is the side wave of three-phase induction motor. Inside we have the rotor. Let us consider a squirrel cage rotor for the time being. So this is the end ring. You can see this is supplied by three-phase supply. This is three-phase supply, and there is a shaft. In this shaft, a mechanical load will be connected. So if we increase the mechanical load, that means if we increase the tau exerted on the motor, then motor will start producing the same amount of torque. And that is why in our previous class we wrote that tau produced by the motor is equal to tau load, that means load torque. When they will be equal, the motor will run with a constant speed if it falls in this stable region. We divided our torque speed characteristics curve into two portions. One is stable and another is unstable. This region is unstable region and this region is stable region. To run the motor with a constant speed under a certain load, the motor must run in this region. We can vary this load torque and motor will start producing exactly same amount of torque in order to run the motor stably. If we reduce the torque, the produced torque will also be reduced by increasing the speed. So when the motor's produced torque is reduced, then the speed is increased. If we increase the load, that means we increasing load torque, then motor's speed will be decreased and the motor's produced torque will also be increased. So in this way it works. Now if we plot the load torque line, for example we are plotting load torque line here, and this is tau L. The operating point will be at the intersection point of these two. That means motor will produce exactly same amount of torque equal to the load torque. So this will be the intersection point. And the corresponding speed will be this. This is the rotor speed. Now, if we increase the load torque and if we provide this amount of load torque, what will happen? This intersecting point will no longer be the operating point, rather the new operating point will be this, and the new speed will be this, which is the reduced speed. So motor is producing more torque as per the requirement of the new load torque, and the speed of the rotor will be reduced. When we increase the load, what will happen? The operating point will move from here to here. It doesn't stop here due to inertia, and it overshoots and it crosses this line. Once it crosses this line, motor sees that I am producing more torque than the load torque, so again it comes back, and it comes back and forth. In this way, after some time, with a damping effect, it comes to a stable position. So if I draw this, so due to overshoot it goes up, and after some times it comes to the stable position. Now, magnitude of this overshoot depends on how abruptly you are changing the load. Suppose if you make sudden change of the load, then the peak value of this overshoot will be higher. And if we make the gradual change of the load, then this overshoot will be lower. In this way, we can reduce the overshoot by changing or increasing the load gradually. Now, under running condition, if we increase load more and more, we bring it here, then the new operating point will be here. That means we are giving more load torque, and motor will also produce that amount of torque as long as this is in the stable region, and the speed of the rotor will be decreased. If we keep increasing the load, what will happen? As long as it's in the stable region, then motor's speed will be decreased and the motor's produced torque will be increased. But if the line crosses this maximum point, that means if we provide higher amount of load than this maximum load, then motor won't be able to run with this amount of load and motor will be stopped. And this point is named as maximum torque. Sometimes it is also referred as breakdown torque. So we have seen different conditions for different loading conditions. Suppose this is tau L1, tau L2, this is tau L3, this is tau L4, and this is tau L5. Now, one thing you need to understand, under running condition, the motor is capable of running with tau L4 amount of load. But when the motor is stopped, as we can see, for these two cases, tau L3 and tau L4, this amount of loads are higher than the starting torque. So with this amount of load connected, if we switch on the motor, as the starting torque is lower than the connected load torque, for example, we are considering this tau L3 condition. This tau L3 condition, that means the load torque connected is higher than the starting torque, so motor won't be able to start. So what we need to do, we need to reduce the load, start the motor, so it will come to this operating point under running condition. If we increase the load gradually, and if we come here up to tau L3 or tau L4 load, then motor will be able to run under running condition. But once the motor is stopped with this amount of load connected, if we give the power supply to the motor, as our starting torque is lower than the load torque, motor won't be able to start. We'll plot this torque speed characteristics curve using octave for a typical set of values. For the simulation, we'll take the value of rotor resistance equal to 0.2 ohm and the value of x2 at a standstill condition can be taken as 0.7 ohm. The value of E2 prime equal to 80 volt. The number of pole per phase will consider 4 pole per phase machine and F equal to 50 Hz supply. Well, this is the editor panel of Octave. I have written the equation for tau r, that is 3 by twice by ns into s e2 prime square into r2 divided by r2 square plus x2 prime square. Now, in order to run this code, we need to define the value of constants. So we took the value of R2 to be equal to 0.2 ohm, then the value of X2 equals to 0.7, the value of E2. Actually, I'm not writing prime here to make the notation simplified. Actually, in equation, this is E2 prime and X2 prime. That means reactance at standstill condition and induced EMF in the secondary side at a standstill condition. So E2 we are considering equal to 80 volt. We'll consider 4 pole per phase system. Now we need to define what is NS, because we have NS here, that means synchronous speed. Synchronous speed NS equals to, we know, that is 120 into F over P. Now what is F? We need to define it here. F is the supply frequency, that's 50 Hz. So F equal to 50. Now we need to define one more parameter, that is NR, rotor speed. Rotor speed, we'll consider this as variable. So we'll take this value starting from 0 with a certain increment. I'm not writing the increment now, and the final value will be the NS, synchronous speed. So in between we need to write the increment. Let's take 50 steps from 0 to NS. So we may divide it by 50, and the value of NR is defined. Now in our tower equation there is no NR variable, instead we have S. So we need to figure out what is the value of S from this NS and NR. We know our slip value equal to S equals to NS minus NR divided by NS. Is there anything left? Oh well, let me write clear all, so that all the previous variable will be cleared, and close off. That's it. Now let's put the plot. So plot NR versus tau R. Let me run, save and run. So I need to give a name here. I'm giving torque versus NR. There is an error. Let us see what is the error. Oh, here instead of putting comma I have put dot. Now I think it's supposed to be worked now. That's it. We have got the shape that is desired. This is the starting torque, and motor starts from here and it follows this line. It goes to the maximum torque point. Then the torque starts reducing, and the operating point depends on the load torque. Suppose the load torque is 0.5 Newton meter. So what will happen? At this point there will be a line, and will be an intersecting point. So the motor will be stable and will run with a constant speed that is lower than 1500 rpm, and this will be the operating point. Next we'll see the effect of changing rotor resistance on torque speed characteristics curve. Previously we saw the effect of changing rotor resistance on starting torque. We saw when we increased the rotor resistance, the starting torque increased. When R2 becomes equal to x2, then we got the maximum value for starting torque. Then if we keep increasing the value of R2, it starts decreasing. Now for running condition case, we'll see what happens to this characteristics curve. So from this equation, we'll take different cases for different values of R2 and we'll see what happens. Before I plot this, here we plot the same for different R2 value using Octave. Let us modify our previously developed code. Here we took one fixed value R2 equal to 0.2. So let me take this from here to here. And for R2 equal to 0.2, we'll plot the corresponding value for tower and we are naming it tower 1. And same we can plot for R2 equals to 0.4. Let us increase the rotor resistance. Then the same equation will name the second variable as tower 2. Then if we keep increasing the value for R2 equal to 0.6, then let's name it, this is tower 3. Next value will take R2 equal to 0.7. Why am I taking 0.7? Because x2 is 0.7. We are considering R2 equal to x2. So we'll copy and paste here. This is 0.7. Then we'll keep increasing. We'll take R2 equal to 9. Now let's, this should be named as tower 4. Should be named as tower 5. Finally, we'll plot inner versus tower 1, comma in versus tower 2, comma in versus tower 3. Inner versus tower 4. Inner versus tower 5. So all the plots will be shown on the same figure. So let's see. Now that's it. We have got different plotting. We can see as we increase rotor resistance, initially for R2 equal to 0.2, this was the figure. Then for R2 equal to 0.4, the starting torque increases. Then for R2 equal to 0.7, the maximum torque acts as starting torque. Then for R2 equal to 0.9, it starts decreasing. So we have got the idea how it looks like. Now let us redraw the curve with the change of R2 value, and let me demonstrate elaborately what happens when we change the rotor resistance. So what we got from our MATLAB coding, in x-axis we have nr, in y-axis we have tau r. So for initial case, this is the R2 value and this is ns, that means rotor speed equal to synchronous speed. This is the first starting torque, tau s1. This is the peak line. What we saw, if we increase the rotor resistance, the torque speed characteristics curve looks like this. Here the maximum peak shifts from right to left and the starting torque increases. This is tau S2. So here this is the case for R2 prime, which is greater than R2. Now if we keep increasing the value of rotor resistance and if we take R2 equal to X2 value, this peak will come to the starting point and the maximum torque will act as maximum starting torque. So the curve will look like this. So this is R2 double prime, which is greater than R2 prime, and this R2 prime is greater than R2. So this is tau S3, which is the maximum starting torque, and we are getting this for the condition when we are considering R2 equal to X2. Now if we increase the value of R2 more, the starting torque will start decreasing. How it works? So it actually the peak point moves to the left. So as this is not our working domain, so this peak point will come here. This peak point position, but as nr equal to 0 here, so we can see our torque speed characteristics curve will look like this, and this will be the starting torque, and this is for tau s4, and this is the case for R2 triple prime, which is greater than R2 double prime, which is greater than R2 prime, and R2 prime is greater than R2. So if we keep increasing the value of rotor resistance, then the starting torque will be decreased. So this is the torque speed characteristics curve for different values of R2. Remember, we cannot increase the maximum torque. Remember, we cannot increase the value of maximum torque by changing the value of rotor resistance. However, the position of maximum torque can be changed by changing the value of rotor resistance. However, we can increase the starting torque by changing the rotor resistance. Let us take this figure in the next page. Here one thing I want to mention, that whenever we are considering the changing of rotor resistance, that means we are considering the own rotor case. Remember, it is not possible to change the rotor resistance for squirrel cage motor. For a particular load, suppose the motor was running with R2 rotor resistance and we have this amount of load. So this is tau L. Let me name it tau L1, the load number 1. So corresponding speed will be this. Now if we increase the load under running condition, then the operating point will go up, as we saw in the previous page. At this condition, if I draw the new load line, this will be the operating point and this will be the corresponding speed. So this is speed 1, this is speed 2. Now at this condition, if the motor is switched off, we can see this is tau L2, load torque 2. This load torque is higher than the starting torque. With this amount of load connected with the motor won't be able to start if we have this tau S1 as starting torque. Now we can do one method. We can reduce the load, then start the motor and increase the load again. However, without releasing the load, we can start the motor. How? By changing the rotor resistance. That's why we use on rotor type case. When we have higher amount of load, then what we can do, we can increase the rotor resistance so that this starting torque goes up. After increasing the rotor resistance, if we give the supply, then as this starting torque is higher than the load torque, motor will start. But what will be the operating point? It will follow this blue line. The new operating point will be this. So under running condition, we can see for the same amount of load, the speed is lowered. This speed is much more lower than this black intersection point. So once we start the motor, once it comes here, that means motor under running condition. Under running condition, we know that it can run with this characteristic curve as well. So under running condition, what we can do, we can reduce the rotor resistance so that the motor operating point moves from this point to this point. In this way, we'll be able to start the motor without removing the load. And under running condition, if we continue running with this R2 prime condition, then the speed will be decreased, which is not desired. So in order to increase the speed, or in order to regain our previous speed, under running condition, we'll remove this rotor resistance and we'll connect R2, or we'll lower the rotor resistance and we'll connect R2 to regain that previous speed. How is it done in industry? I'll show you by showing a picture. So let me write some points. So the point number 1, that is starting torque can be increased by increasing rotor resistance. That is R2. Second point is that if we increase rotor resistance, starting torque increases, but running speed decreases. And third point is we cannot increase maximum torque by changing R2. The maximum obtainable starting torque is maximum torque under running condition. I hope this effect is clear to all of you. We'll discuss after this topic in the next lecture. Thank you.